So far, any questions? Okay. XRD will determine our crystal structure. XRD is kind of the concept that we shine X-rays through the material at a certain angle, and whatever X-rays come back out of that will help us determine the crystal structure, like the plane spacing, also the lattice constants of our crystals. These crystals are grown in a particular monoclinic type of structure. Monoclinic meaning that the A, B, and C axes are all different, and then the angle in between is not 90 degrees, so it's some offset degree. So think of like a rhombus kind of tilted. So our crystals that we measured for the XRD, it's kind of hard to see on these, so maybe I can go back. We take these nice sharp crystals, it's kind of one here, typically here, and we will measure them on the 001 plane in the XRD machine. So, and that kind of confirms that we see these Miller-Lindsay peaks. So from this, we can see that determinant on the peak sharpness, the crystal quality. So far we haven't really determined the ideal metallocene crystal yet. The next thing is we're going to do is talk about Raman. Raman, these are just descriptive figures. This is not quite my expertise of things, but it's nice to show that depending on the Raman modes, you can see how the molecules will vibrate, how they twist, how they rotate, depending on, and we observe these peaks, which are also seen in previous literature. Next thing we have is the FTIR and Raman comparison. So in our PBT crystals, we confirmed previous literature where we've seen that these assigned peaks occur. We also see some new features in these physical vapor transport crystals. Designated in the blue areas, those are just new peaks that we observed. We also observed some new peaks in the kerosene zinc crystal. So, and this is kind of just giving an extra little background into this. So depending on how the vibrational modes, how they breathe and the rings breathe, you can see these features in like the FTIR and the Raman, depending if it's asymmetric or symmetric breathing of the molecules. All so far is just characteristic of confirming a lot of previous literature with some new modes that we've seen. And this is a table of all the Raman and FTIR modes. Some of them are new that we observed, characterized here. We also see some other new modes that we mentioned, like this VCR range. But here's where the interesting part comes in. So for our purposes, metallocene crystals, depending on the color of them actually, tells a lot of which one of these is going to be our best host material for the chromophore. Now, I said chromophore absorbs energy and emits in the visible spectrum. Well, cobaltocene nearly being black, if you were to deposit some kind of chromophore in this material, well, it'd be hard to excite because that cobaltocene will absorb your emission, or absorb the excitation energy. If somehow it got inside the cobaltocene, that excitation energy, the cobaltocene will reabsorb it. So in other words, this would not be a good emitter. Nickelocene suffers from the same kind of problem. It's a dark color. Although it's slightly translucent, it's still similar kind of properties. Ferrocene, although this picture does not quite do it justice, it's more translucent. You can kind of see through it in this case. And also the ferrocene is more naturally colored, like it's orange, or chromophores, as you remember before in the previous slides, are orange to reddish. And you mix them together, the absorption is going to be mainly from the chromophore, and it's going to be emitted from the chromophore. In other words, the ferrocene is not going to absorb this. Another detail is dependent on the metallocene type. Ferrocene, as documented in the literature, lasts a very long time. When I grow a sample, we can expect it to last a month, or even more, depending on the crystal thickness. Nickelocene will decay in about a week, and cobaltocene will decay usually in a day. And that's due to the metal ion size, with cobaltocene being the largest nicotine being the second, and ferrocene being the smallest. And that helps with the stability of that molecule. Okay. So, I could have introduced that slide first and ruined the whole surprise for everybody, but I saved it for last. So, I just want to conclude that growing these crystals by PBT, we saw some characteristic features of vapors grown and solution grown crystals. We also seen that they have a monoclinic crystal structure. We also kind of cataloged some new modes, and we have determined, as me and Bumps have discussed before, that ferrocene is going to be the best post-metallocene crystal. Okay. Any questions before I move on?
What's a vibrational mode?
A vibrational mode is the allowed, depending on how that crystal or depending on how that molecule is constructed, there's only certain allowed modes because of the symmetry of that crystal. So you can have forbidden symmetries, which say that you cannot have that vibrational mode. So kind of glossing over from the FTIR and the Raman, that will show what allowed vibrations are in the crystal, and you can kind of do a little crystal inference on the crystal structure. So if you have stronger peaks, it means it's tighter, more broad peaks, it's more vibrations are allowed. So, yes?
How come the crystals don't last longer?
So the oxygen can get into the crystal, and oxygen is like a reactive species. So reactive species, it means it likes to take electrons away from things. These metallocenes, as I said, they're van der Waals kind of bonding. It's not like ionic bonding or covalent bonding. It's like a sharing of kind of the wave function, from my best understanding of it. So these are also organic in nature. Organic materials tend to degrade because of the reactiveness to oxygen. I'm not saying that inorganics can't react to oxygen, but in the quantum dot sense, like I assumed a while ago, they're inorganic, and they last a very long time because of their inorganicness, like years. Like a funny story with me and Bumps, who actually explored going down a little bit of a quantum dot route, and we still have them in our refrigerator when we got them like 2 years ago. And I can put them on a spectrometer and still measure them, but not in the case of ferrocene.
Thank you.
Okay, really cool stuff. Stuff that's more aligned to our research. So we identified the ferrocene host matrix is going to be the best metallocene metal matrix or system. Now we have these two chromophores to choose to dope inside this. And doping means I want to take this molecule and have it inside this unit cell in both cases. So what we are going to do is our goals is we're going to do kind of the same measurements, except with a little bit of Raman, no FTIR, no activity or anything. But we want to characterize how that chromophore sits in that unit cell or that matrix there. Then we're going to compare the photoluminescence. Photoluminescence means that since these are chromophores, they're going to emit visible light. We can see this on the spectrometer. This is more like foreshadowing into the next, so I don't want to get ruined. Anyway, so we're going to grow these also with PBT. However, I don't want to take complete credit for this idea, because I'm not sure if anyone else has done this, but I cannot find any literature, but this is an idea that I came up with. So we're going to use the same settings for growing ferrocene, but we have an independent heater that is wrapped around with heat tape around the chromophore. Now, why would I do this? Remember, as I said a while ago, the sublimation temperature of each material or compound is different. The chromophores, they're very stable and resilient compared to the ferrocene or cobaltocene and nickelocene. So, just to run through the scenarios here, if I did not have this independent heater, I would grow ferrocene crystals, but the temperature is too low to grow or deposit any tetracene or rubrine inside these crystals. Conversely, if I set the oven to 300 degrees Celsius and had the same setup, the nucleation energy for the ferrocene from the oven is much, much higher, so all this vapor will go right out the tube. You won't grow any ferrocene. you'll grow pure tetracene rubrine. So that is the purpose of this dual heating zone. And as a secondary kind of feature or benefit to us, we can also not only purify the ferrocene, we can purify the chromophore. That'll help with our device characteristics and device emission. After we prepare the samples grown by PBT, at Bumps's lab, we have a cryostation. This cryostation will cool down samples down to 10 Kelvin or even 4 Kelvin. In the case where we run at 10 Kelvin just to preserve the life of the Montana cryostation. And that will come up later. But I want to talk about, so we did Raman spectroscopy of the dope samples. And from the first figure, the red one being the a rubrine sample with a high doping. High doping meaning that there's a lot of rubrine deposited inside that metal scene, the ferrocene. We have also a low doping that's in the green, and we have a pure rubrine crystal, and then the outline is a pure ferrocene crystal. So first of all, we see this broad background emission in the cases of the background emission enhancement from the rubrine doped samples. And in the case of figure B, we also have this is a tetracene doped ensemble molecule, where also in the ensemble, or meaning the doped sample, we have an enhanced background emission. And then we have like the characteristic ferrocene crystal itself. Now, reason being that this enhancement of the background Raman emission, when the chromophore is doped inside that host matrix, it's separated from other chromophore neighbors. So it becomes more monomeric in nature. Monomeric meaning like it's acting like an individual molecule that's not interacting with that neighbor. Ferrocene also kind of like due to the color that we were talking about earlier.